So recall last time I see this, there's this recent conjecture, some kind of, I mean, it's not, again, not the ultimate form of the categorical version of a local Langlands conjecture, which, but this is already something actually quite, I mean, it's somehow, on the one hand, related to more classical formulation, but also has some very concrete applications and you know, like can say something very concrete. So and it's as I mentioned, it's actually merged from the several people like Hillman, there. Benzwei, Chen, Nadler, Hillman, Chen, and also there's like more general from Farks and Shelter, and some idea also from myself. So I'll just state this. Let me first state this. In this particular case, is suppose G over F is local field, F local non-Archimedean. And this is, let me assume this is quasi-split. Yeah, I probably need to fix additive character from this to some ring of coefficients, which so will be, I mean, just for simplicity, I just see it in these two cases, but you know, lambda should be really should also allow the actually more general coefficient. So then the conjecture is suppose G is quasi-split and equipped with the pinning. Borel torus. Then there exists a natural fully faithful functor from this category, which I denote by A, which I defined last time. The category represents finite generated representations of G of F with coefficient in lambda to this stack of local Langlands parameters. Let me, for example, write the L group here. So, yeah, I could also write C because I was already explained it last in yesterday's Q&A session. Sorry, not here. This is the coherent sheaf, fully faithful. So satisfying some natural conditions, which I'm gonna talk a little bit more. L is not equal to P, although I guess we will also heard some version for L equals P later in letters. L not the residue characteristic. Yeah, but some version L equals P will also some natural compatibilities. Conditions. And I guess I will try to list some of them. They're basically definitely an incomplete list, and those properties will not also uniquely fix such thing, but I'll try to. So, yeah, I'll start try to mention some of them. Some are, which are some of them are like the categorical analog of the classical. I mean the classical local Langlands correspondence formulated in Olivier's lectures. So I guess maybe the first one I would like to say is if G is torus, this is some like I mean. Even just the simple case, G is GM. This is given by this again given by class field theory. Yes. So actually, you can check in this case. Actually, the ring of global functions on this guy is basically the Haeckel. It's just or maybe write it in this way. Smooth functions, compact supported smooth functions on F cross with lambda coefficient. Once you have, and then this stack issue is very mild because the GM conjugation action is basically trivial. So you can literally write this stack as this just some affine scheme times some classifying stack. So it's not the. So then basically like representations are. Finite generate representations are modules here, but there's some finiteness assumption making these are coherent sheaves rather than general quasi-coherent sheaves. Okay, and actually one can also do more for arbitrary torus. You can normalize it in a way. So G equals torus. I mean, in general, there's some Galois cohomology playing around to upgrade this to the case of torus, but. You can imagine, at least for commutative group, you need to fix such thing at the beginning. And then the second one is compatible with parabolic induction. Which I want to mention a little bit in details, because this is something starting like this categorical thing start from. Looks a little bit different from the classical way you see how this something correspondence is compatible with parabolic induction. So in this first of all, this parabolic induction in representation theory side is just as usual. What do you know? You have this representation. Of if it's suppose I have some G, you have a parabolic and the Levy. Then you have the usual parabolic induction, something from representation of M. Let me go to representation of G of F. This is just the usual parabolic induction. Okay, which I will not questions. No. Okay. So which I will not recall. But the whole point is in this Galois side. What this is a representation. So representation. Theoretic side. But on the Galois side, things are slightly different. So in the Galois side, traditionally one would consider the dual group of the Levy embeds into the dual group of G hat, and maybe then pronounce this to a homomorphism of L groups. But to do actually geometrically, what is really better is still consider the similar picture as follows. You have the corresponding dual parabolic, which embeds into G hat, and then you have a corresponding projection to Levy, which then this can be pronounced to a now morphism of kind of a stack of corresponding representations. And then these are, I can't remember what I want to, R, Q, or maybe this is R, Q. Some morphisms, these are morphisms. And then one can see some properties of these morphisms to guarantee the operation. What I'm going to write down is like the valid, but anyway, let me skip that. I will just then see this so-called the spectral side, the spectral parabolic induction.
Sorry, can you say what you mean by p hat?
P hat is it's for. I mean, this is defined by some rule system here. Bunch of thinking diagram.
Literally the
Yeah,
okay.
yeah.
Thanks.
Yeah. This was also actually already explaining like the Borel's the original Covanes article about the parabolic group of dual group. So yeah.
Thanks.
Yeah. So then it's supposed to. Then one can actually define the following is like maybe spectral. Yeah. Parabolic inductions. It's actually defined as it's going to be a functor from the category of coherent sheaves here to category of coherent sheaves here. So it's defined as upper Schritt pullback and upper lower star push forward of from here to here. Okay, so you need some words actually some work need to be done to see these morphisms are reasonable. So this operation are preserves coherence. Just 1 minute. So just like this map, if you want to send a push forward, a coherent sheaf is coherent. It's something like a proper morphism. Okay. So.
Just a naive question. When you say coherent sheaves, you mean derived category?
Oh, yes. I need to derive. I need to derive everything. Yes, derive. This is a statement of derived category, not a statement of.
And the second naive question: can you describe the image of the finite length representations?
Finite length. I mean, there's irreducible representations. For even let's talk about the irreducible representation. Yes, so I hope I want to see one phenomena, which is a little bit here, which makes actually somehow it's related to from exactly the set theoretical bijection of classical Langlands needs to be. I think there's still one needs to understand it in a better way, which I don't. I'll try to mention one. Like even in the spheral unramified case, I'll mention. Hopefully mention one example. Okay. All right. Okay. So in fact, the whole point is really pull back, push forward, not just embed the dual group of M to dual group of G and push forward coherent sheaves. That's not actually compatible with this. Not supposed to be compatible with this functor. So yeah, this I should say this kind of thing is actually familiar with in geometrical Langlands, but probably in the classical thing, people don't consider in this way. I might say the third thing I might, I mean, depends on the time. Maybe let me mention is that on this category of representations. Oh, by the way, you should also send finite generated into finite generated. This is something into. On here, there's like Bernstein called on the category of representation of p-adic groups, there's some duality, like Bernstein would call like cohomological duality, but probably other people call Bernstein-Zielinski duality, which is basically a duality functor from this category to itself. And it sends a representation pi to just a harm of G, but of course derived harm of pi to the full Hicke algebra, which is you just consider the all compact supported functions on G with as a bimodule over itself. Yeah. So you take a harm with respect to the left GF action, so the remaining harm space has a right GM action. So this actually did nothing on those compact induction. If you have a compact induction, lambda, it actually literally goes to itself. But it's a contravariant functor. It's not an identity functor. So, and then the claim is actually this functor should be compatible with this kind of duality. If you first take the duality, logical duality, then take this fully faithful embedding, it's going to be the same as you first take this fully faithful embedding and take the so-called, some kind of modified version of this Gorthan-Dixier duality. Okay, so understand, because you can talk about the usual Gorthan-Dixier duality. This is like a reasonable. Actually, I mentioned yesterday it's a classical complete local intersection. So, in fact, it's even better. It's Gernston. So actually, the canonical bound sheaf actually is isomorphic is a trivial sheaf here. So but I need to do a modification which involves this Gardin involution appeared in Raphael's talk. So actually, so this is so yeah, maybe I should also mention here. So we do have this Gardin involution from G to G itself. Not Gardin, right? Chevalier. So it sends a, like, actually I want just do this dual side. Chevalier, sorry, not Gardin. Yeah, it sends basically dominant co-weights to W0, dominant weight, taking the minus, sorry. This is how you do it. Or maybe you think about send the representation to its dual. Okay. And of course, such data induces automorphism. It induces on the dual group, so it induces automorphism of the stack. Okay, and then you wanna compose the usual Gorthan-Dixier duality with this particular involution. So Chevalier. What's the notation usually when you use? Huh? C. So then composed with this C. So sorry, let me write this. D prime is C. So this is kind of a categorical incarnation of the classical expectation, or we've now proved in many cases that the local Langlands should become compatible with this duality, contragradient duality, or what? Duality. And maybe there's a long list, but I want to maybe mention two. Maybe let me mention two. It's one, another two. Give you some flavor. So, or maybe how should I use it? Let me first do. Okay, so just do. The other thing I want to say is classically, people think about the G adjoint group acts on G F, and which induces action of this group. This note I can't remember where I borrow this notation E, which is G adjoint F modulo GF modulo the center of E. This group then will act on the, let's say, set of smooth representations of GF by conjugation. Yeah. So, but this acts on here. But actually, maybe let's do, because we categorize everything. Maybe let's do better. Just consider this is just a stack quotient, and think about this is a Picard groupoid. Actually, also acts on this category. And on the other hand, this is what the can remember the notation. Let me denote by maybe not some. What would be the good notation for this group? Okay. Let's say Z. Okay. But actually, this is now I need to remind myself. Yeah. So actually, this. Now I need to.
You're looking for the kernel of H1 ZSC into H1 Z dually?
Yes, I could see that this way, but I want to embed this into the do side. I want to sort of embed this into the right in this way, coherent sheaf of some log, but I want to take ZG hat or something like that, which even in the case of finite group is kind of complicated. So how about this? Let me ignore this compatibility. This is something. It's sometimes Tasho could do it immediately, but I need to always think carefully. And so let's do the other compatibilities. I want to, okay, I haven't seen where I use the pinning. So actually the pinning and the additive character produce your Whittaker data. And so you can have just the Whittaker thing. So if I have pinning, I take the uniform radical of Borel and take this, the pinning actually provides a canonical morphism from U to GA, and then you take F points and compose with this precise, maybe I write precise 0, 0. I get a Whittaker character of UF, and then I take the induction of it. It turns out that this is does not land inside this category, because it's not finitely generated. It's basically can be written as a union of all these finite generated modules. But so it's not there, but I can do some kind of incompletion. Then what you will get is not literally a coherent sheaf, but a sort of an incoherent, some kind of incoherent, inductive limit of coherent sheaf on this stack. And this stack, this is exactly structure sheaf of this stack. G of int. So, or maybe let me just write in this way, but this is in.
The question was just whether it's BF or GF.
Oh, G. Yeah, sorry.
Okay. And you don't take compact induction, right?
I don't take, I don't take the compact induction, I just take wait. You are right. Actually, probably I want to take the compact induction here. Yeah. This is in algebraic version you always use, but still it's not the finite generator. It's a union. Yeah. thanks. Actually, if you take the full induction, it's a projective limit of something. You take compact induction, it's an inductive limit. It's beta B. But so it goes to structure shift, and I should tell you this structure shift actually is not a coherent shift. It has a support on infinite many components. But this stack has this disjoint union of infinite many components. Coherent shifts are only supported on finite many components. So there's this compatible. And maybe for global application, the important thing is if G is unramified, and then the pinning actually also determines a hyperspatial subgroup of it. So here, like G of O is hyperspatial. Determined actually by this by pinning. B. Then we expect the compact induction of GO to GF of the trivial representation. Like this, this goes to the structure shift of unramified part of the parameter. So I probably need to explain this this unramified thing is. So recall this stack is defined as
Xinwen, there's a question.
Yes.
Sorry, what does coherent mean if the structure sheaf is coherent?
The coherent. What does coherent mean? So the stack actually is an infinite union, like it's increasing union of a stack of finite type, and the coherent means it comes. It's a shifts only come from some finite type thing.
Okay.
Yeah. Yes. That's exactly that. Yeah. So yeah. So this is something you can think about. I said the stack of local systems is some disjoint union of something of finite type. So think about locally finite type, but it's better really think about just something in stack or something. Yeah. Okay. So recall I have this way group mapped to the 10 part, which and then mapped to just the one generated by Frobenius. So then you take the corresponding homomorphism. I mean, you take the corresponding representation stack. You get the so-called the unramified part, which we call it's basically you can think about. Let's see. Right, let's see G split. For simplicity, it's just the G hat mod G hat up to conjugation action. Because I said that this is just this space is if you forget the up to conjugation, consider all homomorphisms Z map to G hat. So that's given by G hat, and then I modulo conjugation. So
that's a closed immersion of hom Z G hat into the hom WF G hat. That's really fine last time.
It's a closed immersion of. You mean this one?
No.
Hom.
Hom Z G hat embedded into hom WF G hat.
Yes, but here I only consider Z.
Yeah.
I don't need the Z hat. Yes.
I understand.
Yeah. And then, yeah. This goes to the corresponding thing is actually I'll denote by 10 because it factors through the 10 parts. 10, and this is the whole. Okay. And this is a closed immersion, actually. It's sort of a irreducible component of this, and this is actually open and closed. So it itself is already a bunch of union of connected component. The reason is actually the difference here is already just a pro P. So when you take the consider further representation, this just a split out. Okay. Okay, so this is something we expect, and of course, as I said, you can list a bunch of more conditions, but including something I couldn't figure out at the moment. But
these conditions actually calculate uniquely?
it does not. It does not, as I mentioned beginning. A better way when you, I think people believe if you really go to the categorical version and admits this spectral action, then there's a way to characterize it uniquely. Basically using spectral action compatible with parabolic induction and Whittaker normalization. That probably would be enough. But there's some, okay, I mentioned this word spectral action, but it will really appear later in Schultz's lecture. But that is a really complicated thing and very implicit. So it, huh? This is reasonably easy and concrete. It doesn't use any fancy thing. But it doesn't characterize it uniquely. But I could actually tell you what another thing you can think is how do you characterize, determine this? Because the category is essentially generated by one element, just the full Hecke algebra. So you really need to specify where this full Hecke algebra go. There are also some conjecture where it should go. Not in general, but for some groups, one could produce some conjecture. Okay?
Sorry, so maybe you said this, but is this functor A supposed to depend on the choice of character, like Whittaker datum or something?
It depends on the choice of, so I always fix psi 0 and let this pinning to vary. And all possible pinnings exactly some group, torso under the group I was writing down. So I was, at some point I was trying to write how this is compatible, but then I get confused myself. So yeah, will not do it.
So do you expect like all of the tame thing to be in the structure sheaf of the tame thing to be in the image as well?
Structure sheaf of the tame thing will be in the structure sheaf is a tame part. Actually, it's going to be a idempotent component of this. So it will actually land in the first part of the approximation of this Whittaker. You project this Whittaker representation to actually the depth 0 representation. That would give you, supposed to correspond to structure sheaf of tame. Yeah. Actually, yeah, I could also add, for example, you want the category of depth 0 representation actually faithfully embed into just the coherent sheaf here. But let me not to do that at the moment. Oh,
the tame part also finite type?
This is finite type. There is only finite. Essentially, this group is, inside here, this is Q, gamma Q. This is a finite generate group. So there are only finite many components, but there could be really a bunch of not. Okay, so that's okay. So I talk about few consequence and expectation, consequence of this conjecture, and a little bit of evidence, and so forth. Okay, so let's start with the easiest case is which somehow, let me just do this. Yeah, no, yeah, I just erased, but I will also discuss the example really why the spectral side of parabolic induction needs to be defined in this way to get something correct. So the first situation is, let's say G unramified. Let's even, yeah, G even for some simply, I say split. And then we look at this functor supposed to send this compact induction G of O of lambda. It's supposed to be just a structure sheaf of O unramified part. Okay? So what does this mean? We actually already could see a lot if you have such thing. So first of all, as we can, if this is fully faithful, that means the endomorphism of this object in the category representations should be the endomorphism of this object as coherent sheaves on that stack of Langlands parameters. So explicitly, this would mean, so this would mean the endomorphism of this guy should be just isomorphic to the endomorphism of this. However, you need to be careful. This is always a stack, but I'm considering this a coherent sheaf on a bigger stack. So I need to take its endomorphism on the whole thing. But fortunately, the whole thing is too big, but as I told you, the tame part is already open and closed. So I can just, it's enough to take its endomorphism inside here. Okay, so I need to have this equality. But what does this mean? The left-hand side is something well known. It's just a spherical Hecke algebra. So let me write it in this way. Except this spherical Hecke algebra, if lambda is a field of characteristic P, actually might need to be derived because we are computing this in the derived category of endomorphism. But if lambda is a field of characteristic 0, this is projective objects. So it's endomorphism. It's really just honest algebra, no derived. But on the right-hand side, then this is so what you would get is something like this. This would be some kind of enhancement of the classical Satake isomorphism, which after if you take the H0, just you get the classical spherical Hecke algebra. And on the other hand, if I just take H0, now I'm taking a coherent sheaf on the substack. Let's just consider the general situation on Y. I'm considering endomorphism of OZ on Y. It may have derived structure, but it's H0 is just a global section of OZ. So this is going to be just this. Okay? H0 is always this. So what does it mean? It actually means this taking H0, this we would basically recover functions on this stack of unramified Langlands parameters, which would be exactly conjugate invariant functions on G hat. And this should be just the classical Satake. Okay, but okay, then even in characteristic 0, this actually tells us more about the classical Satake isomorphism, because we always the left-hand side is always just concentrated on degree 0. The right-hand side, a priori need to be derived. Actually, it turns out that means it should concentrate on degree 0. So let me just for you to those people number theory oriented.
So have you switched away from the C group by taking maybe a square root of?
Yes, yes. It's kind of isomorphic to. I switched from C group to G hat because of Q&A section yesterday. There's a way to switch between this. But you have a square root of Q. Somewhere, yeah. But this Satake isomorphism depends on the square root of Q.
G splits surely does not. G split.
It's still needed in some cases. Yeah, C group might be like a PGL2. Yeah, but you can switch it Otherwise, I need to write C group, but then add some condition. It's not that. So, okay, so, but actually, even in characteristic 0, it tells us more. So this is basically, one can, actually, this is, so even, and let's just consider the simplest case, G is GO2, or maybe even PGO2. Actually, this, for those people are number theory oriented, this stack of terminal ramified Langlands parameters, the geometry is kind of Fermionian, and I mean, I should say, at least for the term part, it's kind of, the picture is actually like this. So in this term stack, there's also a part called the unipotent part, which you just require the term inertia acts, the monodromy of term inertia is unipotent. In characteristic 0, actually, that one is already a connected component. In general, it's more complicated, but in characteristic 0, this is already a connected component, and its geometry looks like this. So I have a stack of unramified parameters given by just Frobenius conjugates class, and then there's this so-called the Steinberg component, where the monodromy is principal unipotent monodromy. And they intersect at this point, something like up to conjugacy given by this, or maybe because I switch, maybe square root P inverse or something like that. Okay, so this is so in other words, what you are doing is you are taking a coherent sheaf just supported on this component. It's an irreducible component, and compute its endomorphism in the whole stack. So then a priori, to compute its endomorphism, you need to take a resolution and compute it. So miraculously, the higher cohomology endomorphism vanishes. So actually, this is really a theorem. For GO2, you can prove it directly, but in higher over it is the, for example, Ri. This is 0 for I bigger than 0. So, which for GO2 you can check it directly, which is you need a little bit computation of how to resolve the shifts. But when you go to higher dimension, it's actually a pretty complicated thing, the geometry, because you have a lot of unipotent conjugates class, and their intersection is really complicated. But this is still true in characteristic 0. But actually, more interesting happens is when gamma is FQ. And in this case, actually, some form of now this is again the left-hand side now is truly derived, okay, and the right-hand side then depends on, of course, the congruence between L and Q. There's some problem. The right-hand side then should also be derived, actually. Some version of this, I mean, different version of this actually first appear in Tony's some papers called the spectral Hecke algebra. It's not in this form, but somehow could be shown to be equivalent to this. And so if lambda is FQL bar, it's also, so maybe I just remark everything should be derived. No, everything will be truly derived. And hopefully, I'm not sure, but maybe some later lecture will talk about, because there's some lecture about derived Hecke algebra stuff. This will appear. And this isomorphism, I guess, modulo some unpublished some work. It's expected to be true. Okay, like people should be. We probably have heard something. This holds in general, but this is somehow how this this formalism actually already makes some derived Hecke algebra appears, even in this simplest situation. But it's not the end of the story. But suppose I should stop at like 12:30 on that on that clock or something like that.
Something like that. It's 12:20, but this clock is a bit fast by 3 minutes.
3 minutes. Okay, 20 something. Okay.
Yeah, so 12:25.
25. Okay. So yeah. Right. So now we can see a little bit more. I have this compact induction. Okay. It's supposed to go to the structure sheaf O of G hat mod G hat. Okay. This guy lives in this stack, but it maps to the GIT quotient. Okay, map to the GIT quotient, where this is like the space of semi-Satake parameters, the usual set of Satake parameters. And actually, this this compatibility with classical Satake means under this equivalence, these functions on here act on this sheaf should be exactly the way acts on how the classical Hecke algebra acts on here. Okay, so if I choose a point, I should get the following thing. Again, let's say G is basically GO2. This is to give you some feeling. Should tensor with this Hecke algebra, classical Hecke algebra, with chi, this character chi. I mean, one thing I did not say, but it's true, is it's supposed to commute with co-limit this functor. I mean, it should commute with all finite co-limit, but yeah, in this case, it's already actually, it's additive functor, it's a finite co-limit. So this suppose actually then correspond to, you take the structure sheaf of the fiber of this guy. Okay. So this is two things is of course a priori everything needs to be derived. I need to take the derived tensor, and here I need to take the derived fiber. But fortunately, this map is a flat map. This is a classical Chevalier map. So here I could take an underived thing, and actually it's known this module is module over this Hecke algebra is also flat. You don't need to derive it. But actually, I could, if I have time, I could give a simple proof using this why this is actually flat. Why you don't need to derive it. But anyway, let me. In this equivalence, actually one can remove both derived. It's a classical thing, but this is a bit. Questions?
I was just saying that now I know what to ask you during the Q&A. What is this like?
What is this? I mean, in general, it's hard, but over QL, I'll give you. I could give you a proof pretty soon. But it's even over QL, it's non-trivial. Okay, so but see now there comes this thing. It's a little bit interesting. It's this guy. Let's again suppose this G is GO2. There's 2 points actually. A little bit strange. It's a point, and I write this. If chi is given by actually the Satake parameter corresponds to the trivial representation, I guess under our normalization, this is its corresponding Satake parameter. Yeah, like then this one becomes not irreducible. It has a quotient. It's a trivial. It's a quotient. Okay, but this guy actually. The fiber is always contains one orbit except 1 point. When the chi is just 1, 1, the origin, the fiber actually contains 2 orbits. One is the origin and the unipotent orbit. Okay, in this case, This is non-irreducible. It has a trivial quotient, but this is just one orbit. Just after stacking, this is a point. Just literally has one point.
Whatever is the, you mean the same thing, the tensor?
Tensor.
Sorry.
Yeah.
So this is a point. In this situation, this actually is an irreducible representation. I hope I'm not wrong. I asked Suku yesterday. So this is an irreducible representation, and its Satake parameter is given by this parameter. But this irreducible representation will correspond to a coherent sheaf, not support on the really the semi-simple Langlands parameter, but like this, it's really supported on this orbit, the whole orbit. So this, but this becomes has two orbits. So this suggests this categorical form of local Langlands actually is more, the relation of this with the classical local Langlands is more complicated than people might thought. Even in this simple case, it's actually irreducible. May not the original one might think the irreducible go to some coherent sheaf who has some support and it has a unique open point. That would be the Langlands parameter it is assigned to, but it seems not exactly the case.
Okay. So how do you see the two irreducible representation above this form?
Above from here. That actually involves bigger, the unipotent, like I think if I remember correctly, this composition series has trivial and also Steinberg here. And it's actually Steinberg will correspond to coherent sheaf support also on this component. So then there's a complete extension of them, so making, when you do the extension, this coherent sheaf only support on here. Okay. The irreducible, so the irreducible correspond to the coherent sheaf is actually, I just want to say, the coherent sheaf correspond to irreducible is really, could be complicated. Okay, right. This is the first example I want to discuss.
Sorry, does this fact that you just showed us have any representation theoretic consequences? For example,
what comes? I mean, why this phenomena? Actually, it would be good to discuss that.
Yeah.
Sorry, could you repeat this statement? So, why is a naive expectation? What is it?
So yeah, so maybe so I guess for a while people somehow, at least my expectation is this categorical, how to recover the categorical form of Langlands to the classic form. Irreducible representation would correspond to some coherent sheaf. And such coherent sheaf should have some support, a closed substack. Coherent sheaf has support. And its expectation would be that support has a, because it's a stack issue, the support has a unique open dense orbit point. That originally was my thought how the Langlands parameter of the irreducible representation should go.
Is that still true for supercuspid?
Supercuspid might be okay, yeah, but the problem already appears for the unramified parameters. Make me one needs to think more what happens really. But on the other hand, there's like strong evidence that this should be true. For example, I say the Hicke algebra really match. So this categorical form should. So the other situation I want to give you this example too is.
When people say geometric Satake correspondence,
it's geometric Satake is a different thing. It's different thing. it was mentioned yesterday in Zhu's talk very briefly. I don't know whether I will have time to talk about this afternoon. Let's see. Talk a little bit more. This is kind of decategorification of the geometric Satake. Right.
I thought that was the usual Satake.
It's usual Satake, but more. It has some derived. Usual Satake won't be able to allow you to do this derived part. Yeah, but the usual Satake is a decategorification of a geometric. Okay. All right, so time I have the second example. So I want to take G again to be just a GO2, but I want to talk about one representation, which is I take the parabolic induction from this standard Borel, and then go to the torus, and take the unramified universal unramified representation of the torus, and do the parabolic induction. Okay, so let's see what it should correspond. Yeah, so then I take basically the compact induction of this unramified of lambda, and then do the parabolic induction to B to G of F. Then under what I was all this compatibility. By the way, one can show this is basically, you can also write this induction is a compact induction from Iwahori subgroup to G of lambda. Okay, this is, you can think about in this way. For GO2, it's kind of easy to prove. But. Okay. So where does this go? Then, as I said, recall this picture. This unramified representation then should support on the stack of for torus. Then it's the unramified part, which is just the structure shift of O hat, O hat. Then, I mean, this guy should go to here. This inside the log. Okay. And then I need to do this spectral version of this parabolic induction. So what I'm doing is I'm pulling back the structure shift here, and then push forward. But I mentioned somewhere that everything shrink pull back and sorry.
So to be clear, your downstairs should be CG.
C. That's right. And actually, because everything could happen in the temp part, you don't need to go to this full infinite many component. You just need to do this. So you're just doing this. That's the shift you're supposed to correspond to here. Okay, but I mentioned somewhere that actually all these stacks, the canonical bundles are trivial. So you can think about this as a canonical shift, or shrink pullback would be just canonical shift, which then is also some trivial thing. So you can just think about this as like O of, but this is an unramified part. So by definition, the fiber product is the unipotent part of the Borel. So it's just this. Okay. So this is defined as a Cartesian by Cartesian. So this is has a name originally I learned from Benzvi. It's called coherent because it's analog of Springer's theory. It's called coherent Springer sheaf. And also, I guess also independent considered by Hillman. So I guess his motivation also comes from actually this kind of picture. So it appears in this way. So then suppose this representation will correspond to this. And again, you can play the game to the first question is what are the the Heck algebra, because this is supposed to be a fully faithful functor. So the endomorphism of this, which then it's just the Iwahori Heck algebra. Let's see, if this is QL, characteristic 0, so I don't need to derive anything. That should be actually just the endomorphism of this guy. Let me denote coherent spring, maybe unipotent part. That's kind of so expectation is like this, and actually over QL, this is already proved by Benzvey, Chen, Hillman, Nadler, and also Hillman had some partial result in this direction first, and also there's some work of Himo Tamir and myself. We have some kind of different proof. This is okay, actually. So this is actually, in some sense, quite striking, because this guy is a priori is not a coherent sheaf, it's complex. And then you take its endomorphism, it should be a priori also, again, should be highly derived, but again, it's just concentrated on degree 0. Over FL, it's, I think there's still a long way to go to prove this in general. But I could give you the picture, just how it looks like in the simplest case, GO2. Yeah. By the way, let me just mention this log of CB, the stack of Langlands parameter with value in B. This is really a truly derived object in general. And to make this correct, you really need to think log of CB is a derived stack. Okay, so the basic geometry is actually the G is GO2, and let's see, lambda is QL. It turns out what happens is I analyze this stack downstairs, this unipotent. It's roughly speaking the intersection of two components intersect at this point, P1. And it turns out what happened, this is a Steinberg component and this unramified component. And it turns out what happens, sorry. You are considering, over the unramified parameters, what does this mean? You have a Langlands parameter, you map to G check, but then I need to make this Langlands parameter land in the Borel. So, but over the unramified part, G check is, the parameter just depends on only one element. So I have one element in G check, and I want to choose a Borel contained in it. That's exactly the classical Grothendieck-Springer resolution. So it turns out what happens over here, this log B unipotent, is you have this Grothendieck-Springer resolution, which is a two-folded cover here. They meets here, okay, at this point 1, 1. So it probably has something to do with some ramified picture, and then there's like this P1 over this fiber, okay. This is classical Grothendieck-Springer resolution, the picture. And here at P1, this Steinberg component actually has a unique, because I already have a unipotent, regular unipotent element. It uniquely determines a Borel. So actually there's only one component. So I don't know, the picture just looks like this. It's a little bit complicated. I mean, then you can just compute it once you have this. The geometry upstairs is not that bad. It's and then let me just tell you the result. Actually, is just this coherent Springer sheaf. Could do exercise. It's really just the two parts. It's a direct sum of a sheaf on the unramified part and the direct sum on the unipotent part. Okay. So so in particular in this case, you see this sheaf is sheaf of is abelian. It's literally coherent sheaf, not a complex. Okay. So yeah, actually. Right. So actually, this is let me just say this is not a special feature of GL2. One can prove actually it's the work of Xinwen Zhu. Myself is at least the G split. It should be true unramified, but let's see, this coherent sheaf. And the lambda is QL, characteristic 0. This is really important. At the moment, this is a sheaf of up. It's concentrated on degree 0. Degree 0. Okay. So, yeah, it's literally a sheaf of a coherent sheaf, not a complex. Although it's push forward of structure sheaf from the derived stack, but at the end, it's a sheaf. So, yeah, actually, let me give this. Yeah, let me leave this to QL station. How to use this to prove flatness. It's kind of easy. Okay.
Can I just ask, sorry, asking the question, but is this somehow the relation to the kind of the classical realization of the Hecke algebra in the Kunz-Ginsburg?
That's actually a different realization. It's really so. It comes from actually this Chris Ginsburg. You first categorize it into the so-called Bezukov-Nikov equivalence, and then decategorize it in a different way to get this statement. So their realization is by sort of some K theory of Steinberg. Yeah, but this is different. Okay. I talk about this thing, some example, and then I wanna. So, how about in general? So I should also mention. I should also make a remark. I give you some example. I like some. If you assume this conjecture, there's some predictions, and we verify some of the predictions. Hopefully, give you some evidence of it. So let me just make a remark. If for GON, actually in this same paper, in this Benzvei Chen, Nadner's paper, they basically construct this functor H, essentially using all the because we know a lot of about the local Langlands for GON, so somehow they use this to construct a functor. Yeah, using let's see, or maybe even C, because in this same situation, this stack actually makes sense over C. Let me write QL bar, something like that. Using what's known on the classical local Langlands for GON and some input from this coherent Springer sheaf, they construct it. But somehow this construction is inexplicit. It's not we really hope is some better way to understand this. And a particular question is, what does this A of, I said, if I want to really describe this functor, probably I need to understand where this guy goes. I mean, this is, it's not a finite general module, but it's an in-object. So this should give you an incoherent sheaf somewhere. So it's really, actually would be really nice to know some conjectural formula of this in general for arbitrary group. If you know that, you actually essentially know this, where this functor should go. But unfortunately, we don't know. But there's a, first of all, there's some, I guess, original, some version of this come from the modular, like patching method that have some this, like Emerton-Helm has some form of this, where this sheaf should be. But also I have this conjecture is one can, there's a purely spectral side description of this sheaf. It's, you take, I mean, but I'll talk about this, mention this conjecture a little bit more. It's on this log. Okay, so in this case, G is GON. You can consider all possible Galois representations. It's essentially all the possible Galois representations up to conjugacy. But you can cook up some other bigger weird object. You consider a chain. This is like V1, V2, Vn. So I mean, not inclusion. Sorry, it's important to consider just maps. So Vi is a I-dimensional representation of W. And then you consider such map and push forward. So the conjecture is this sheaf of this object. Let me actually write this, give a name of A of G. It's,
What is the map pi?
pi is just remember the last one. Yeah, just remember the last one. A of G is pi of omega. Of this, if I denote by the stack, I guess I denote by Wn. Maybe this is it's kind of W is not good. Why? Let's see. Okay, so this is sort of the conjectural formula purely from the spectral side, but it should be. So let me just end with a few remarks. So I would say, even in general, you know such a functor. It's really, for many applications, it's important to know exactly which this functor will send some representation to which coherent sheaves. Okay, and from all this example, we see these are this coherent sheaf somehow should obtained from some push forward of maybe dual Langlands sheaf or structure sheaf from another space to it. So there's no, I mean, general conjecture about that, but this seems to be the case in all examples we encounter. Just maybe I will give one more example in afternoon's lecture, but it should be something like that, hopefully in general. And it's, for example, for general, for a Levy K, you can ask, what is this? Where does this goes? And for general level, we don't know. But you can also do more. For example, you can also consider what appears in this in this relative Langlands program. You consider representation of this, and or maybe more general, like the x now K is xf, maybe function as representative of gf. Where does it go? So I hope, presumably, I mean, I should say all this, the prediction of this space usually comes from like physics. The physics has some prediction, like then first they have then people doing geometric Langlands first understand it, cook up some spaces. Actually, I should mention this conjecture. In geometric Langlands, there's a analogous conjecture by Brabham and Finkelberg. They have some conjecture in geometric Langlands, but it has direct arithmetic analog, so we can formulate it. So hopefully, I guess, presumably we'll hear some talks later on in Venkatesh's talk. Maybe he will also tell us how to cook up sheaves on log correspond to this kind of representations, using purely from the spectral side description. Okay, I stop here today, in the morning.
Any questions for
I wanted to ask, I mean, this is very close to what you just said, but is there any expectation for what the essential image should be, or just for the same reasons you don't really have a conjectural expectation?
No, like for this description, for GON, you have this. Maybe for some classic group, you can use some quiver diagram to produce something similar, but I don't know. For example, for exceptional group.
Classical motivation about the total normalization, like why the top sheaf will match to the top sheaf.
Yeah, that's always the expectation from geometric Langlands.
And then how do you
But you can verify actually in the tame case, in the unipotent case. You
can verify something.
Can calculate the endomorphism of each side? The endomorphism ring of each side?
Yeah, exactly. The endomorphism ring of each side. This is exactly. Is it not proven, but or proven is endomorphism Whittaker module should be just a ring of regular functions on the stack of like Langlands parameters. I remember like Schneider and or there's definitely some work in classical work in this. I just don't know whether it's already proved or probably not. But this exactly predicts the endomorphism of Whittaker.
What's the relationship between the kind of derived enhanced Satake and the geometric Satake?
It's come from some. I mean, actually, yeah. There's some. First of all, there's some derived geometric Satake, and and then somehow you use some general formalism called the categorical trace. Probably you should arrive to this kind of statement. Yeah.
Does this conjecture should depend somehow on the choice of site?
Oh, but you mean here or?
I mean, here in this definition of A, it depends on site.
Depends on psi 0 is actually very mild. It's like actually it's only you can always normalize this conductor is like O or something. It's like some Zima 2 choice only. And all other choices come from this pinning, but for GON, all the pinnings they are all conjugate. Yeah.
Okay, maybe we should let Xinwen.
Maybe one more question.
Oh, one more. Okay, please, last one.
Alright, so I was confused by this. You said that there was an iris representation whose image is not the closure of one point.
No, it's a closure, but it's like this unramified representation it's a closure of something, but the point is not a semi-simple point.
Okay.
Okay, so let's thank Xinwen again.